lot, Andy, and thanks everyone for coming out and braving the weather and coming here. Of course, as Andy said, I think the city is capable of much more than that. Yeah, I'm excited to be here today, and I'm going to talk just about what we kind of see as the major trends for big data that are kind of happening right now, and how they are affecting Apache Spark over the next year. And I'm going to just start a little bit to say with what happened last year. You know, a lot of things happened last year, but at least for Apache Spark, it was a pretty good year. We had basically the biggest thing that happened was the Spark 2.0 release, which came out with a lot of very important features. So in particular, Spark 2.0 stabilized the structured APIs for Spark, things like DataFrames and SQL, which are kind of the foundation for a higher performance execution engine underneath, and it also brought some pretty significant speed-ups to all these things through the work happening in Spark SQL and Tungsten, as well as SQL 2003 support and quite a few other features. Last year, we also began structured streaming, which is the new higher-level API for streaming, and we also continued to see really fast growth of the project. For example, the number of just Spark meetup members worldwide went up by more than a factor of 3, and that's really amazing to see given the project's already been out for about 6 years, so it's continuing to grow super fast. And I just looked at this number, and today it's actually more than 300,000 members just on meetup.com. So really cool to see. And just to highlight a few of the kind of applications and use cases people talked about last year, we had some really cool talks at Spark Summit about these. So first of all, at Microsoft, they made a number of presentations about using Spark streaming inside Bing to process, up to tens of terabytes of data per hour, as well as inside Office 365 analytics. And then at Facebook presented about their use case using Spark SQL to accelerate some of their very large SQL queries. And they were getting these pretty big speed-ups over Hive. And you got to keep in mind, Facebook is the birthplace of Apache Hive and also of Presto. So they definitely know SQL engine. So it's really awesome to see Facebook contributing to Spark SQL and embracing it. And they've contributed a lot of really cool patches. And finally, on the enterprise side, there's continued adoption in pretty much all kind of industries where people have significant amounts of data. One example that we highlighted at Spark Summit was Capital One, which is a Databricks customer, and they were using Spark to basically implement more advanced credit card fraud analytics using Spark and Graph Analytics, and they were able to take a much more sophisticated model and run it quickly enough to be able to find these applications. So you'll see talks from many other companies today about cool things that they're doing with Spark. So what I want to focus on is a little bit different. I just want to talk about what are the kind of the newer major trends for big data applications happening, if you just step back and look at them a little bit. And these are the things that kind of drive the direction of, at least the work I'm kind of trying to be involved in with Spark. And so I'll talk about the work that we're doing to address them at Databricks and also elsewhere in the community. And I'm going to talk about three trends, kind of hardware and the compute bottleneck that's beginning to play a bigger and bigger role. Users, basically democratizing access to big data so more people can use it directly. And applications and the push towards production applications, which is what drives a lot of the work in streaming and low latency serving and things of that nature. And I'm going to start with hardware. So it's fair to say that hardware is basically what drives most of the work in software and in applications and computer systems. And if it wasn't for significant changes in hardware, we wouldn't be here today. What happened basically 10, 15 years ago is your computer stopped getting faster at a fast enough rate that you could just take your application from the previous computer and move it to a new one to keep up with data. So people had to come up with all these distributed computing models, and none of the previous software works, so they had to rewrite it and come up with programming models such as MapReduce and Spark. So that's the only reason we're doing any of this stuff today. Otherwise, we'd be happily running Python and MySQL and whatever and talking about ultra high scale for those. But hardware isn't standing still, and there are interesting things happening that could be kind of a similarly large shift in the next few years. So if you just look at what's been happening in hardware, this is 2010 when Spark was first released as open source. And this is kind of what the world was looking at back then, what a server would look like. So you had most of your storage on hard disks. These maybe have 100 megabytes per second of bandwidth, maybe a little less. Your network in your data center was 1 gigabit per second, and your CPU cores were about 3 gigahertz. Now, if you advance a few years to today, your storage, at least kind of short-term storage in something like Spark, will almost certainly be on SSDs, and it's a factor of 10 higher performance. And your network also, commodity data center networks are 10 gigabit all-to-all bandwidth. Some are a little faster than that as well. But your CPU cores are essentially still the same speed. And sure, there are slightly more cores, but not a factor of 10. So basically, this is what we have. I/O has gotten 10 times faster, but the computing remains a bottleneck, essentially. It's become extremely slow in comparison. And the reason for this is because basically the end of frequency scaling for CPUs. You can't really make them run more cycles per second without using up lots of power and essentially melting your chip. So hardware manufacturers are doing other stuff. For example, they're building these simpler and more parallel devices like GPUs, FPGAs, many cores, and things like that. But obviously, using those, moving applications to those is just as hard as it was to move them to a cluster. So there's a lot of work to do. So basically, a summary is, kind of 2005 to 2010, when MapReduce and Spark were being designed. I/O was the name of the game, and we did all the stuff you need to minimize I/O. Network locality, compression, in-memory caching, all of those were in the first version of Spark. But now, compute efficiency matters even if you've got a data-intensive app like a SQL query. And it's even harder to obtain it if you try to use the new types of hardware that the manufacturers are putting out. So what are we doing about this in Apache Spark? Of course, we're looking at this and making sure that the project will continue to take good advantage of future hardware. And the effort to do this is Project Tungsten, which began about 2 years ago to optimize Spark's CPU and memory usage using two things: binary storage format that escapes kind of the JVM, and you're no longer tied to the limits of that, and runtime code generation. So Spark's binary storage format just stores data, as a sequence of bytes, same thing you'd have if you were writing kind of an application in C. And it's a lot more compact, and it's outside the Java heap, so there's no garbage collection. Basically, we can manage the memory ourselves, so that makes it more efficient. And then Spark's code generation takes your code and your high-level APIs like DataFrames or SQL and compiles it into currently Java bytecode that accesses that raw data directly. So basically, it turns into kind of pointer arithmetic working on this data. So you don't need to program this low-level like pointer chasing stuff, but you still get pretty high performance. And Tungsten's made a big effort, made a big impact, especially in 2.0, where we added this whole stage code generation where you fuse together all the operators in a query into one piece of generated code. So in a lot of queries, we see kind of a factor of 10 speed up. This is the same thing we hear from users who try 2.0 for their queries. And a second thing that we've optimized pretty heavily is input and output. In this case, the Parquet, we got about a factor of 10 speed up there too by making it convert stuff directly to this nice binary format that we understand. This is often a bottleneck, so this is something that we want to make better. But this isn't the end of the world, and there's a lot of this isn't the end of the work. And there's a lot of exciting stuff still left to do. So some of the things that we're working on now, and other people are working in the community, are first and foremost kind of solidifying the interface between Spark and native code or external systems to allow them to pass data in an efficient way. So we want to have a standard binary format to pass data in and out of Spark, and we could use the existing Tungsten format. Maybe we could use something like Apache Arrow. This is still kind of to be figured out. And we also want to use the format for data sources so that anyone writing a data source can get the same optimization we got for Parquet by making it produce data in the kind of native format Spark will understand. So this is one thing that I hope will be happening this year that will really kind of move Spark forward, because it will also make it easier to push data to these accelerators like GPUs or to libraries like TensorFlow and so on. The second area we've been looking at is integrating with these deep learning libraries, which are some of the first to really heavily use this accelerator hardware in very common applications. And Intel has put out a library that they'll talk about today and tomorrow, BigDL. And at Databricks, we also have open sourced an integration with TensorFlow. So we're working on basically making all of these great ways to run to run deep learning in Apache Spark. And finally, I think one final thing we would like to do is add these accelerators, whether they're kind of many cores or FPGAs or GPUs, into Spark Scheduler as a first-class resource. So I think this remains to be designed, but this will be another thing that, that makes this type of work easier in the future. So that's kind of the work in hardware. What about users? So the most interesting thing we've seen in terms of users, kind of since the Spark project began, is the need for more and more types of users to easily access big data. And this was a goal of the project from the beginning, to make it easier. Initially, we started with software engineers. We said, hey, why would you have to write 100 lines of Java code to write a map function? Maybe you can write like 2 lines. And then we moved to data scientists and SQL analysts. So this is something that's had a really big effect on usage of Spark, and we still think there's more to do there. And just as a simple example, just in the past 2 years, here are some numbers we got from surveys that we ran at Databricks of users, usually at Spark Summit, to see what languages they're using with Spark. So in 2014, most of the usage was Scala and Java, especially for data engineering, writing kind of these big complex programs, which is great. And we love to see that. And we tried to make that job very kind of doable using Spark. But if you look just 2 years ahead, there's kind of almost an equivalent number of users in Python and R who are usually kind of a new class of users that are doing data science and are still getting a lot of work done with Spark. They're also, sometimes they're transitioning these applications to production and so on. So this has become kind of a major use and kind of a new community of people using the project. And on top of these two things, everyone uses SQL. Whether you're using data engineering or Python or Scala, you'll be doing SQL as well. So what are we doing about this in the project? Well, this is, again, a thing we've been doing explicitly since the beginning, try to make it easier for more people to access these clusters. So the first thing is Spark SQL. Spark SQL only really came out basically in 2014, so it's actually quite new as an engine, but it's the most heavily developed component. And in Spark 2.0, it actually supports more of SQL 2003 than any other open source engine, and there's still tons of activity in the community to improve both functionality and performance. So that's the thing that everyone uses that we wanted to make really solid. And then the second idea is these high-level APIs that look similar to single node tools, but allow us to do kind of non-trivial optimizations for the distributed setting. So things like data frames and machine learning pipelines and the Python and R APIs. So this is a major focus for us at Databricks, and I think for many other groups in the community going forward. And there are some really cool things going on. In the SQL and DataFrame side, we have cost-based optimizations coming into Spark, likely in 2.2, maybe 2.3. And this is work that originated at Huawei, and quite a few other companies have contributed to it. And we also have improved data sources in terms of, for example, JSON parsing, CSV, and so on, that are coming in 2.2. In terms of Python and R, this is something that we're doubling down on to improve both performance and usability, and there are lots of like little issues in there and new APIs to do. And finally, kind of a crazy but kind of useful idea is to make Spark easier to run on a single node. So we see a lot of people develop stuff on their laptop, and maybe they want to connect it to a cluster, or maybe they just want to process data locally somewhere. So, and that's actually kind of hard to do with Spark today because you need to install it on a single node. It's kind of annoying. So we're actually working on publishing it to PyPy as a standard Python package and to the equivalent package archive in R, and also on optimizing them for these large multi-core servers that people like bring back the data to. And one idea is, if you're using the multiprocessing package in Python, which is a way to launch, multiple threads to compute stuff, why not use Spark instead? You'd get these higher level operators like map and group_by and so on. So that's the kind of thing that we want to drive towards, make it as easy to do as importing that. So we'll see how far we get along that path. And then the final thing I want to mention is applications, and especially the move towards production applications. So this is, again, something we've seen across a lot of different users. Big data is moving into production. So what do I mean by that? Well, when it started out, big data was just about collecting some data you might kind of throw away in other cases and analyzing it offline. And this was actually the whole notion of a data lake, for instance, was like, hey, let's just pool some stuff, let it like simmer there for a while, and then once in a while we'll go in and pull stuff out of it and see what we can find. But now, over time, people find, applications that actually work pretty well. Like, hey, there's some report we can compute that's super useful, or there's some model we can train that then we can use to improve our business or our application. And then the next thing they ask is, well, how do I turn this into a production thing? I'm computing this report with Hadoop. It was awesome, but I could only do it once a day. Can we do it in real time? So that's what motivates a lot of streaming. Or I'm building some kind of model. It seems useful. We're predicting or like we're detecting credit card fraud. Now can we put it into a serving system and update the stuff in there in real time to serve values out? And currently, it's really hard to build these because you have separate systems for streaming, serving, and batch. And you've got to hook together these distributed systems, maybe like a Spark, HDFS, and Redis, or something like that, or MySQL. Hook them together into an application. And when we talk with users, they say most of the work they spend is actually in hooking them up, in making sure that, when you read stuff, you only read it once, and you don't forget where you were when the app crashes. When you push stuff to your serving layer, it better be consistent across it. You don't want to just do that update halfway, and so on. So what we'd like to get to is, instead of you hooking them up by hand, have a single high-level API that lets you build these so-called continuous applications that can not only compute on data inside Spark, but also update and interact with external systems in a consistent way. And this, I think, would save a ton of people a lot of time in building these applications. So this is what we've been trying to do with structured streaming. So structured streaming is this high-level API built on DataFrames. It makes it easier to write streaming apps, but it also comes with these two powerful properties. It comes with these transactional interactions and kind of the internal API to work with files, databases, message queues, lots of other systems in a consistent way. And it also comes with integration with batch and interactive queries, so you can reason about what happens in a bigger application that uses this and other forms of computing. And one of the ways that it does that is through the API, which is this really high-level API. Basically, you give us a DataFrame query that computes what you want, and then you tell us to do it incrementally. And we'll make sure that you get the same answer all the time that you would have had if you just ran this query once at one point in time. So we'll keep both the inputs and outputs consistent with that. So just as a super simple example, if you've got a batch job, this is something that reads some JSON data, does an aggregation, and writes it out as Parquet. It seems really simple, but this is the kind of job where, like, if it fails halfway through and stuff, you'll get weird partial results left over sometimes. If you just have this kind of job, you can convert it to a streaming job by just changing the read to read stream, and same thing with write. And Spark will handle those transactional updates for you and the state management and so on. So you just tell it what you want to compute, and it will actually do this stuff. And we've been, structured streaming just came out kind of in the second half of 2016, but we've been working both at Databricks and with quite a few customers to use it. And we have a few pretty cool use cases that we want to talk about today. We'll have talks on these later on as well. So at Databricks, we've been running our log analytics pipeline on it since the second half of 2016. We believe strongly in kind of eating our own dog food. And then two customers, Viacom and iPass, have really cool applications that they've talked about publicly, or they'll talk about here today. Viacom's powering real-time metrics for all of their properties, including things like Nickelodeon and MTV, and iPass is monitoring thousands of Wi-Fi access points for security and quality purposes using structured streaming. So you'll hear a bunch about them today. And there's still lots of work happening. There's integration with more systems. We have JDBC is on the roadmap, and unified access to Kafka for Spark 2.2, so just easier access. There's new operators. Map with state is a highly requested one that's coming in 2.2, and session-based windows. And we also have a lot of work planned on performance and latency. Now that the basic engine is in, there's a lot we can do to improve this. So expect to see some pretty exciting work in this area. So that's kind of what I wanted to talk about, just a tour of what we see as the major trends in big data. Hopefully you see them as well, and what we're doing about them. And just to summarize, these seem like three different trends, but these are things that we're all integrating together in Spark 2.0. So we're making sure that we have an efficient engine, that it can be accessed to all these high-level APIs by lots of new users, and that it can be built into end-to-end apps. And I think this is the most exciting thing about the project for me, that we actually have this big vision of trying to solve the problem end-to-end instead of just a little piece of it in a corner here or there. So thanks a lot, and enjoy the conference.